Okay, so what I want to do today is talk to you about how to solve this problem. So this will be homework 20. So you can see it's going to be our cardboard beam. On the left side here, we're going to have a cross section that's half an inch thick, 3 inches tall, and of course it's prismatic. It doesn't change along the length. Also, I pointed out that this is incorrect information. The span is 20 inches, but the length of the beam will be 22 to give us an inch on the supports. And then here's all the material properties that we need, and that will work on those. Also, it says don't forget to go back to the project description where we have the equations for how to calculate the sum of normalized weight and displacement. You can see it's a function of displacement and the weight. And then also there's a weight penalty for cost. So we'll come back and make those calculations at the end. So the first thing I want to talk to you about quickly is how we're going to do this modeling in SAP. So before we jump into SAP and just get started, I want to talk to you about this particular model. So what we're going to do is, remember, we have our structure, whatever it is, and we're assuming a pin and a roller. And you remember from our discussion, or the Project 2 description, so the span is 20 inches, and that's going to be the distance to the edge of the supports. And then to have at least an inch on each side for supports, I'm going to assume I have these little 1-inch overhangs on both sides. And that's where that 22 comes from in the description. Also, don't forget that around the center line of the structure, what do we have? We've got the 240-pound load, and it's distributed over 6 inches. So over the middle 6 inches of the structure, I have a distributed load that totals 240 pounds. So what is going to be the intensity of that load if 240 pounds is distributed over 6 inches? Yeah, it's going to be 40 pounds per inch. So that's the load that we can put into our analysis. Now, how are we going to model this? Well, first of all, we want the displacement at the center, so that's going to be a point that we want to compute. So our SAP2000 model will look something like this. So here's our 22-inch length. I'm going to want a node right in the center, so that's where I can query and get the displacement. I'm going to want one here because that's where I can put my pin support, and also one here. And then I'll need another node at this point. So I'm going to have a very strange looking element. I'm going to have one element that's 1 inch long, and then a 10-inch long element, another 10-inch long element, and then 1 inches. See that? Another interesting thing that we're going to have to do is over the last 3 inches of this element, we're going to have a distributed force, right, of 40 pounds per inch. And then really over the first 3 inches of this element, we're going to have another distributed force of 40 pounds per inch. We haven't talked about that before. How do we have a load that's not over the whole element, just over a partial part of the element? So we're going to have to deal with that too. So I want to talk to you about this first before we dove into the SAP2000. This is the model I'm going to build, and then I'm going to apply these loads, and then we're going to calculate the displacement. And we're also going to enter in our property values. Okay? So any questions about that before we dive into SAP? Oh, Okay, so let me do a quick switch back here. And find my SAP 2000. Oh, where is it? Oh, shoot. I have to do it this way. Sorry for this. I do have it somewhere. Where? There it is. All right, so I'll switch back to the computer. So I'm starting up SAP 2000. Sorry for the delay, flipping between 3 and 4 different screens takes a minute. And a couple computers too. I thought this local computer had it, but it doesn't seem to. And thinking. Oh, there we go. Great. All right. So let's go ahead and start. I'm going to go down here in the bottom corner and I'm going to set my units. I'm going to do everything in pounds and inches. Okay. I'm going to go under File and create a new model from the template. And I'm going to create a beam. In this case, I'm going to say I have a lot of spans. I'm going to do everything at 1 inch. So I'm going to say I'm going to have 22 spans 1 inch apart. I know that seems a little odd. No restraints. So now I have a series of 22 1-inch beams. Okay? But what I'm going to do is I'm going to select this set of 10, and under Edit, I'm going to tell them to join them. And that quickly changes that. Let me turn the grid off. You can see now there's my 1-inch beam, and then there's a section for 10 inches. And I'm going to do the same thing over here. Select those 10 elements. Oh, did I do that right?
You said edit and what?
I think I made a mistake and made those 2 inches long, didn't I, instead of 1 inches long?
Yeah.
Okay, we'll start again. So I'm going to go under the new temp, add a new one. No, I'm not going to do it. So I want 22 spans for 22 inches, but I want them 1 inch. It'll look much the same. Oh, shoot.
Do you get rid of this?
I'm making lots of errors. That's good, because I'm recording this forever. This is good to know. So let's start again. 1 inch. Sorry, 22 spans, 1 inch, no restraints. So it looks pretty similar to what we had before. Now these are 1 inch apart. So again, I'll choose these 10, and under Edit, it's called Join. So it'll take all those frame elements and join them together into one. And I'll do the same thing over here on the right-hand side. Choose those 10, and under Edit, we'll join those. Then here on the left side, I'll start with my supports. I'll put a pin on the left and a roller on the right. Okay? We have our geometry. Let's go ahead and set our material properties. So I'll go under Define, Materials. I'm going to make a new material. I'm just going to call it Card B, for cardboard. I'm going to come down here and what is the cardboard's weight per unit volume? It's 0.025, and that's going to be pounds per inch cubed. Also, the modular elasticity from the given material is 58,000. We don't care about the mass. We're not going to do any dynamic work. So these are the two you want to change. The weight per unit volume, which is given as 0.025 pounds per inch cubed, and then the modular elasticity, which is 58,000 psi. That's all we have to do there. We'll just say OK. Let's next define a frame section. In this case, I'm going to modify this one. I'm going to call it what was this? Oh, it's going to be a 1/2 inch thick and 3 inches tall for the problem statement. So I'm just going to say 3 by 1 divided by 2. Why don't we do that? I'm just going to say 3 by 1, just to give me an idea what it is. The most important thing here is that you get the material to cardboard and then get the correct dimensions. So the depth is going to be 3 inches and the width is going to be 1/2 inch. And you can see it draws a little cross section to scale. So I just called it 3 by 1. So again, it's 3 by really a 1/2 inch, and it's made out of cardboard. So we'll say okay. So we've defined this thing called 3 by 1. Say okay. So now I'm going to select all my elements and then assign frame sections 3 by 1. So now you can, it's very small to see, but it does say 3 by 1. I want to show you a feature we haven't really cared about much till now. If you go up here and hit the Set Elements button, and you go down here and say Show Extrude or Extrusion, it'll show you the beam kind of to scale, and if we go to 3D, you can get an idea of not only its width, depth, and it's kind of to scale. Now you'll see it has these gaps at the nose. You'll also notice that we're actually modeling the middle line of the beam. So when you draw a node and you connect it with a line, you're really looking at the center line of the cross section. Not the top, not the bottom, the center line. That looks pretty good. Now we don't have to release any moments because this is a solid material. We want each of these nodes to carry moment and to carry shear. So we're good to go. So I think that's pretty much it. So we'll go up to Analyze and set our options. We still going to work in the XZ plane, so we'll click Plane Frame and say OK, and we're ready to go.
Did we set the loads?
Oh, thank you. We don't have any loads, do we? Well, all we have is self-weight now. Oh, I forgot. We need to do that. So let's go back and go over here and say define static load cases. And load 1 is fine. Let's add a new load. Let's just call it weight. And add that. So we're going to have 2 load cases. The actual load and then just the weight. Right now, the self-weight of the material is in both load cases. So weight, I'm not going to do anything to. I'm just going to leave it alone. But we are now going to go back and add those. So I think it's easier to turn the extrusions off for this part and to go back into the XZ plane. And I'm also going to leave the grid on because I want to tell you that when we apply the load on the first element, we only want the distributed load on the last 3 inches. Okay? Now the way this is going to work, let me switch back to the document camera just for a second. The way this is going to work is like this. So if I look at just this element that I'm drawing right here, and just the fact that I want the distributed load over the last 3 inches, this is one way SAP2000 lets you do this. SAP2000 on an element will let you have what's called a trapezoidal load. And it gives you 4 points to define that load. So what we're going to do is we're going to consider this one of our points, and this, and then this, and then this. So if you can look at those purple points I drew, if you connect those, you will in effect draw the distributed loading. So since we're measuring in this direction, and this thing is 10 inches, our first value would be at x equals 0, the load is 0. And then here at x equals 7, the load is 0. At this one, also at x equals 7, the load would be what? Minus 40, right? Pounds per inch. And then at this point, it's going to be at 10 inches, also minus 40. You guys see that strategy? So with these 4 coordinates, I will open up that menu, we'll enter those in, and you'll see this draw on the end of the element. So let's switch back to SAP. So I'm going to select this element, and then I'm going to go up under Assign. I'm going to do Frame, no, I'm sorry, Static Load Cases, Trapezoidal. When you click that, it kind of looks like the menu you've seen before, but down here in the trapezoidal load is different. Now, we're not going to use relative distance, we're going to do absolute distance. The direction is gravity, that's good, and we're in the right load case, load 1. So at distance 0, I have 0. At distance what? 7, I have 0. At distance 7, I have minus 40. And at the very end of the beam, at 10, I also have minus 40. So those are the 4 points, the trapezoidal load points that we just defined right here. Remember these? Remember those? I just took those values and put them here. So I say OK, and I have it going the wrong direction. I forgot, gravity is down. So I got to redo that. So we'll get a chance to see it again. Fortunately, I can just change the direction to global Z and say replace, and it will fix it. So the same idea, what would we do over here on this element? Well, this element's going to go, we want the load to go from 0 to 3, right? So if I come over here and look at the second element, again, it's 10 inches long. I want the load over the first 3. So this would be our first point. At 0, we want to have minus 40. At 3, we want to have minus 40. And then at 3, we want to go to 0. And then at 10, we want to go to 0. So see if you can figure out those coordinates and enter them back into here. So select the element to the right, assign, frame static load, trapezoidal. We're still in load 1, global Z, so I'm going to start at 0. It's going to have a load of minus 40. At 3, it's going to be minus 40. And then at 3, the load goes away, 0, and at 10, also 0. Everybody see that? Hopefully when we say OK, it'll be in the right direction, in the right place. Yay, it is. So now this is our load scenario for the load case we call load 1. So now we're ready to analyze. So I'll hit the go button to analyze, say run. I'll give it a value. This will be cardboard beam 1, fall 17. Go. And it's running, it's done. There's the displacement. Shape looks good, so I'll click on it and right click, and then there's my displacement. So that's 0.625. That's close enough for me. So let's go back and write that down. So we now have the displacement at C is 0.625, and that'll be inches. What else do we need to calculate the sum of normalized weight and displacement? We need the weight of the beam, right? Remember, the sum of normalized weight and displacement is the beam weight plus the displacement at C times, is it 25 pounds per inch? Anybody remember that? Nobody can remember that. So let's go back and look at our, let's see, I don't know where I put that. Oh, it was on the website. There it is. I don't think that's correct. I think it's 25, isn't it? I think I forgot to update this.
It says 25.
Oh, I got the wrong one.
It says 25.
25? Okay, thank you. Because we're having website issues, I had to go back a page. Okay. So that would be 25 pounds per inch. So we know that's going to go there. So let's go get our beam weight. How do I get my beam weight? Well, if you go look at the output, let's go to the joint forces, J, for a load case weight. A load case weight has no applied load, it just has the self weight. So if I look at the two reaction forces here, that tells me the weight of the beam. So it's 0.41 plus 0.41, so the beam weight would be 0.82. You guys see that? So now I can come back over here, and I now know my beam weight is 0.82 pounds plus 0.625 times 25 pounds per inch. So what's that turn out to be? Somebody do that calculation for me real quick. This is like 15 or something? 15 something? 16 something?
16.445.
And then add that to it. You can see
Oh,
it's not-
I added, yeah. I added
Okay,
more.
so the whole thing is 16 point?
445.
Okay, so 16.44, let's say, and that's going to have units of pounds.
Yeah.
Yeah.
How'd you get those .41 to show up again? On the joints?
You go to J for joint forces,
Okay.
and then pull down the weight load case. If I look at the load 1 load case, what am I going to see? I'm going to see the reactions that include the total force. Right? So if you look at just the joint reactions for the weight load case, which is just the self weight of the material, and I just added those two reactions together. Okay, what's the limit on the strength, the weight, when does this have to be less than? I think it has to be less than 10. Is that right? And this is not less than 10. So this beam is no good. So one of your jobs will be to get the same value I got, and then the second part is to improve that. And I would try to see if you could get it under 10. You can see right away that the beam weight is fairly insignificant compared to the penalty for the displacement. So if you want to get this displacement down, what are you going to have to do? Do you need to make the beam wider or taller? Probably taller. So you could double the height of the beam, still be in the rules, probably only double the weight. What do you think the displacement would go to? Well, that's something for you to explore. Okay? So any questions about that? I'll just get you through the first part.
Are you going to post this video?
I hope to.
Okay.
But this is the first time I've used this software. I have no idea what I've just stuck my foot into.
Okay.
And I'll probably edit that last part out. Okay, so I'll stop here if I can figure out how to stop it. Oh, I think I made a huge mistake.
Did you not press record?
No, I forgot to switch to this, so you won't see any of this. But what I'll do is I'll try to bring it back live now. So you will see something that looks like that now. So as I've been talking on the video, you won't see it, but now on the video you will see the description. So it's going to not work. but it'll be there in some form.